here. So very pleased to have Huy Tuan Pham, who's currently at IAS, but will go to Caltech, right, this summer. Please.
Thank you. Thanks everyone for coming, and especially to Hong and to Sang for the invitation to visit and give this talk. I'm not feeling very well today, so I hope that you can hear me through the mask, but if anything is unclear, then please interrupt me right away. So today's talk will be tangentially actually related to the mini course that I will give next week, but we will take a somewhat unexpected turn, and we will see that our journey will bring about very interesting connections between random graph theory and additive combinatorics. So let's actually begin with this remarkable beginning of probabilistic combinatorics, with this remarkable theorem of Additive. He shows that there exist graphs on big N, a large number of vertices, for which no clique and independent set in the graph have size larger than 2 log N. And if you know, then this he proves is an application to Ramsey's theory. This in particular gives an exponential lower bound to the diagonal Ramsey's number. And in fact, his proof still gives what, even to date, quite close to the best known lower bound that we have on diagonal Ramsey numbers. But even more remarkable is that the proof of Additive result is surprisingly simple. All that you need to do is to consider an Additive-Rangy random graph Gn1/2, or in other words, a uniformly random graph on big N vertices, and then you consider the first moment on the expected number of cliques or independent sets of this specific size 2 log N. You can explicitly compute to see that this first moment is very small, and so in fact, most graphs on big N vertices will have no clique or independent sets of size 2 log N. So this is of course a very simple instance of the first moment method, the first technique that we see in the probabilistic method, and I'll refer to these as the first moment obstructions. So just as a very brief prelude, these first moment obstructions, even though we can see here that they are very simple, they are in fact the main character for the entire discussions that we will have in the mini course next week. So even though they are conceptually very simple, we now know that these first moment obstructions are the main driving force for the threshold phenomenon. So they closely predict when structures start to emerge in random sparse discrete systems like sparse random graphs. And this is the content of the Cayley conjecture that I will introduce more closely next week. These first moment obstructions also have very interesting connections to other fields of study. So for example, to probability theory and high dimensional geometry. Particularly, we'll see that Talagrand selector process conjecture is also secretly about the same first moment obstructions, and these are questions that are of interest in the study of supreme stochastic processes. And while these first moment obstructions are at the same time very powerful and conceptually very simple, well, we'll see next week that actually getting our hands on these first moment obstructions can be highly challenging in applications of interest. So next week we will see how we can employ a lot of ideas and toolkits that we have already had and have already developed in extremal combinatorics to understand the first moment obstructions in interesting non-trivial applications. For today's talk, actually, these first moment obstructions are also still the main character of the talk, but instead of working with the usual Additive-Rangy ensemble of random graphs, we will work in a much more complicated structure, in particular highly dependent ensemble of random graph. That's the random Cayley graph, which I will introduce to you shortly. So in this ensemble of random graph, even understanding just the first moment obstructions of very simple structures like the cliques and independent sets turn out to be highly challenging. And we'll see that they quickly lead us to challenging questions in additive combinatorics or group theory. But quite surprisingly, our final approach to these questions of an additive combinatorial flavor will be based on a perspective that is completely combinatorial and graph theoretic, so much more closer to the probabilistic method than to additive combinatorial technique. And in return, when we are equipped with this new combinatorial perspective, we can actually turn back and improve or resolve important classical questions in additive combinatorics. So hopefully towards the end of the talk, I can show you more of that. So with that, let me actually begin with our discussion of the random Cayley graphs, and we'll be focusing on the Ramsey properties, so large cliques and independent sets. Let me first set up some convenient terms from Ramsey theory. Let me say that a graph on big N vertices is C Ramsey if it has no clique or independent set of size C times log base 2 of n. So in this language, you can rephrase Additive's theorem earlier as saying that almost all graphs on big N vertices are 2 Ramsey. And this corresponds to the lower bound on the diagonal Ramsey number, and correspondingly upper bounds to the diagonal Ramsey number. So as you know, the amazing breakthrough in 2023 of Campos, Griffiths, Morris, and Sahasrabudhe, but also there are very interesting follow-up works after that. In particular, these works now show that there is a reasonable positive constant C for which there exists no 1/2 plus C Ramsey graph. Now, for our talk today, we'll be focusing more on the lower bound side. So we are interested in constructing good Ramsey graphs. And to this end, there is a remarkable problem by Additive, which is still open, for which he asked to explicitly construct C Ramsey graph for some constant C. So we see here that, well, we know that almost all graphs on big N vertices are in fact very good Ramsey graph, even 2 Ramsey. But it's quite remarkable that we can't really get our hand and explicitly draw out one of these graphs. So you can interpret this notion of explicit either in the mathematical sense or in the computer science sense, where you want to give an efficient algorithm to construct a C Ramsey graph. And in theoretical computer science, this is an important motivating question that has led to very interesting progress on constructing pseudorandom generators and so on. But in general, getting to this constant here is still an open question. So let's now adopt this perspective. If we can interpret Additive's question as saying that, well, there is this huge space of all graphs on big N vertices. There are roughly 2 to the order n squared, many such graphs. And we know that if we search over all of them, we can always find a good Ramsey graph. Well, if we cannot directly construct an explicit C Ramsey graph, maybe we can instead try to find a new ensemble of random graph whose support is significantly smaller than the space of all graphs, and yet for that distribution we can still show that we can draw out with reasonable probability a good Ramsey graph. That's one of the partial motivations for the ensemble of random graphs that I will define next, the random Cayley graph. And in particular, we'll be interested in finding Ramsey Cayley graphs. So for us to define a Cayley graph, let's fix a finite group G. It doesn't have to be abelian, it can be a non-abelian group. So given a group G, the Cayley graph is specified by a generating set S, which is assumed to be symmetric. So S is symmetric if whenever G is an element of S, G inverse also has to be an element of S. Now, given this generating set S, we can construct the Cayley graph GS. This will simply be the graph with vertex set G, and 2 elements xy, 2 group elements, are adjacent if x times y inverse is an element of the generating set S. So by the symmetry condition, we see that this will allow us to make this an undirected graph, because xy inverse is in S if and only if y times x inverse is in S. Now, given this definition, we can easily define a natural ensemble of random Cayley graph. So for a given density parameter P, we'll define a random Cayley graph GP as the Cayley graph GS with a random generating set S. And this generating set S is chosen so that each equivalence class GG inverse is included independently with probability P. So in other words, you just include everything independently with probability P in the generating set, subject to the condition that the generating set has to be symmetric. Okay, so let me maybe just give you some quick reasons to convince you why we do care about the ensemble of Cayley graphs. So one of the partial motivations from the Ramsey theoretic perspective is, for example, if we look at the very small number of explicit optimal Ramsey graphs that we know, they all turn out to be Cayley graphs. In fact, they turn out to be a special kind of Cayley graphs, they're called Paley graphs. And understanding Ramsey properties of Paley graphs is a question that is of a lot of interest in both combinatorics and number theory. But in general, understanding the clique and independence number of these Cayley graphs seems to be an extremely challenging number theoretic question. So these random Cayley graphs would give us a good random model, a random analog of the Cayley graph, and it seems reasonable to start by studying them. Also, Cayley graphs and random Cayley graphs have lots of appearance and applications in theoretical computer science, in combinatorics, number theory, group theory, logarithmic theory, and so on. And they also come with very nice spectral properties. So they have strong connections to coding theory, spectrograph theory, information theory, and so on. Okay, so these are just some brief motivations for looking into the random Cayley graphs. So for us today, since we are focusing on a Ramsey theoretic perspective, the properties of the Cayley graphs that we are interested in will be the information about the clique and independence number, the largest clique or independent set, in a uniformly random Cayley graph. So when P is equal to 1/2, I'll refer to G of 1/2 as a uniformly random Cayley graph. You can see by the definition that G of 1/2 is exactly what you get by drawing uniformly at random one of the Cayley graphs of the group. So in particular, we will ask if uniformly random Cayley graphs are Ramsey. Does this property depend on the specific group that we are looking at, or is it independent of the group? So on and so forth. There is also an interesting conjecture of Alon. He conjectures that for every finite group, it will admit a Cayley graph that is Ramsey. So that is C Ramsey for some absolute constant C. And we'll revisit this conjecture also shortly later in the talk. So with that, any questions so far?
Here. So we drop the condition that S is generating set. So I mean, if we randomly choose G and G inverse, then maybe if P is small enough, then maybe we do not choose a lot of elements, and it cannot. Maybe it is possible that it does not generate G. So.
Right. So for here, I am particularly for a second, I don't care so much about whether S generates the entire group G or not. So the graph that you get might not be connected. But well, for this talk, we are going to stick mostly to dense random Cayley graph. And when P is so large, like P is equal to 1/2, anyway, in any reasonable group, you are going to get that S is a generating set for the group. So the graph is going to be connected. Yeah.
Does it make sense at all to look at it the other way? So you start with the Cayley graph and now you just choose some of its edges with some probability? Or, so you don't necessarily include like the G's with a certain probability, but you just start with a Cayley graph and then thin it out?
Right, so you can also consider that. So yeah, so this is what you would get by essentially starting with the complete Cayley graph on the group and then you randomly sparsify it. You can also study, for example, what you suggest, which is to start from an arbitrary Cayley graph, and then study what kind of property will persist if you randomly sparsify it. And this we'll see a lot next week, not for Cayley graphs, but for additionally random graphs. But since for today's talk, we're focusing on Ramsey theoretic perspective, and not sparse random Cayley graph, we will kind of, it's more natural to think about G of 1/2 rather than, yeah. But yeah, of course it's a valid thing to consider. Okay, so with that, let me tell you some of what we know regarding the clique and independence number in uniformly random Cayley graphs prior to our work. Let me mention that, as I briefly alluded to before, these random Cayley graphs, they have very good spectral properties. So you can quite easily show, this is a classical result of Alon and Ruzsa, that these uniformly random Cayley graphs with high probability will be good spectral expander graphs. And in particular, for example, via Hoffman bound, we get some information about the clique and independence number of a uniformly random Cayley graph, just from the fact that it is a good expander. But these bounds are usually very far from being tight, and anyway, extremely far away from the range that we are interested in. So we want to get the clique and independence set to be close to log n, where n is the number of vertices, and these spectral bounds will be much further apart, at least n to the 1/2. So the game here for us is to kind of understand this uniformly random Cayley graph in an explicit way that goes beyond just using spectral properties. That's kind of one of the also interesting perspective here. Okay, but with that, let me say the first result I will state is an old result of Noga Alon. He shows that in an arbitrary group G, the clique and by symmetry, also the independence number, of a uniformly random Cayley graph in a group of order n is going to be of order at most big O of log n squared with high probability. So we are just this quadratic factor away from getting a Ramsey graph. And in general groups, today this is still the best result that we know, apart from two of the very nice special abelian groups, the prime cyclic group and the finite field vector space. So over the prime cyclic group, that's a result of Ben Green and then later sharpened by Green and Morris, they show that the clique and independence number of a uniformly random Cayley graph in this prime cyclic group Zn is going to be of order 2 plus pseudo of 1 log n with high probability. So in particular, it will asymptotically be similar to the clique and independence number of an Additive random graph. And as I mentioned, the only other result that we know is over a finite field vector space Fp to the d. And in this case, Green and then later a sharp concentration result by Mrazovich, they show that the clique and independence number of a uniformly random Cayley graph will unfortunately not be on order log n. They will be of order theta of log n times log n with high probability. So even for these very nice abelian groups Fp to the d, a uniformly random Cayley graph is not going to be Ramsey. And we'll later revisit this mystery. Any question?
I was just wondering if, I was just thinking about the Alon's conjecture on the previous page, but I guess you'll probably talk about it.
Yeah, I will revisit it. From this perspective, it seems kind of mysterious how Alon conjecture can be true, even just in these groups,
Yeah.
while a uniformly random choice fails. But we'll revisit it.
So here, for the finite field, should I interpret P as fixed and B
Right.
grows?
Yeah, you should interpret P as fixed and D is growing to infinity. Yeah. Theta depends on P. Yeah.
So this is all like so Alon's conjecture is weaker version of Arity channel, right?
Or
Of Arity channel, or is it related? If you obey some list of graph, then you have a nice green.
so yeah, I don't know if we can see for this family of Cayley
this-
graphs some
okay, I see.
in
This
forbidden
is about
induced.
random.
Right.
Okay.
Yeah. Okay. So the first result I will tell you about is in joint work with David Collin, Jacob Fox, and Anya Premian, just went up on archive before the year turns. And so we show that in fact in an arbitrary group G, again not necessarily abelian, with high probability, the clique and independence number of a uniformly random Cayley graph is of order at most big O of log n log n. So already the example of the finite field vector space shows that without further assumption, this is the best that you can prove. And we can show that in an arbitrary group, it will never be worse than this. Okay, so as I alluded to before, our proof of this theorem will be just the first moment method. And if you start writing down the first moment for the number of cliques in a uniformly random Cayley graph, then you will see that it very quickly connects to a quantity that is very much of an additive combinatorial nature. So you want to count the number of subsets in a group that have a small product set. And I will now set up the notation and what we are talking about. So given a subset of group elements A, let me define the product set AA inverse. This is simply the collection of all elements of the form A times B inverse, where A and B are elements of A. And you can see quite easily from the definition that you have A is a clique in the Cayley graph G with the generating set S, if and only if A times A inverse, or minus the identity element, is a subset of S. So if we now go back to our model for how we generate the random generating set S, we will see that the probability that the specific set A is a clique in a uniformly random Cayley graph is closely tied to the size of the product set A times A inverse. So in particular, the main result from which you can quickly deduce this theorem is the following bound. We can prove that in an arbitrary group of order big N, the number of subsets A for which the product set A times A inverse is small, is at most k times the size of A, is going to be bounded above by this quantity here. So you can see that there are kind of 3 quantities that appear in this bound, and turns out that you can construct examples showing that all of them are sharp. So this upper bound is sharp up to the universal constant C. Okay, so if we look at this statement, it has nothing to do with a random graph. It is purely a statement in additive combinatorics, or group theory, if you prefer. And in a sense, you can interpret this theorem as being along the line of this important theme in additive combinatorics, which associates structure to sets, subset of a group with a small product set, A times A inverse. Here we are really not talking about some explicit notion of structure, but we want to show that there are few such sets A. So they are in a sense kind of very special or statistically structured. Now, in the previous works that I mentioned, where we know the improved bounds on the clique or independence number of a uniformly random Cayley graph, such a counting step is also the kind of one of the crucial steps along the way in the proof. And previous works take advantage of the fact that if you have very nice abelian group, then you have very strong additive combinatorial and structural theorems from which we can deduce very strong properties about sets with a small product, in that case, like difference or some sets. But it would be very hard to imagine that we have the correct analogs of these results, even just in more general abelian groups, let alone non-abelian groups. So instead, our perspective for proving this theorem is to essentially dispose nearly entirely of the group structure, and our proof is going to adopt an entirely combinatorial viewpoint on the group structure. Okay, so this turns out to be a very useful perspective. So roughly for the remaining part of the talk, there will be several results that I will tell you about. They all turn out to be relying on one key insight. This insight we obtain by looking at these group theoretic problems from a purely combinatorial viewpoint. Then there's one key combinatorial lemma that I will actually only tell you at the end of the talk. So hopefully I think that's the best. I want to save the best for last, and I hope that's a good takeaway message because I think it's really powerful. But before that, I will tell you how to use that key combinatorial result in order to, well, first obtain all of the results that I have mentioned around the clique and independence number of random Cayley graphs, but also we will then see how that perspective allows us to go back and address important questions in additive combinatorics. Okay, so, well, before that, let me tell you what is the combinatorial perspective on the group structure. So to every group G, you can associate to it the following simple combinatorial structure. Let's consider the complete graph where the vertex set is identified with the group elements. Now we are going to give this complete graph a certain edge coloring. We will color each edge xy with the color given by the equivalence class xy inverse, yx inverse. Just want to keep this symmetric, so that's why I put here an equivalence class of 2 elements. You can quickly observe that if you start from a group G, then this edge coloring of the complete graph on n vertices is going to be such that each color class is either 1 or 2 regular. So this is quite close to being a proper edge coloring. Now, a Cayley graph in a group is simply the edge union of some of the color classes. And, well, a subset of the group with a small product set simply correspond to a vertex subset in this edge coloring such that it induces or it determines few colors among the edges in the vertex subset. So we can translate everything that we have discussed before in the group theoretic setting into this combinatorial setting. But what's more interesting, or what's rather surprising, is that just remembering this constraint on the maximum degree of the color classes turns out to be sufficient for us to address the analysis of the uniformly random Cayley graph or other questions in additive combinatorics that you will shortly see. So in particular, we will now define a more general combinatorial model that generalizes the Cayley graph. So in this model, we will start with the complete graph and an edge coloring C for which each color class has bounded degree. I'll call this a delta bounded edge coloring. Now we can define the following model. We call an entangled graph, the edge union of some of the color classes that are given here. And a random entangled graph is formed simply by including each of the color classes independently with probability p. So this is a generalization of the random Cayley graph. And for example, it includes the random Cayley graphs, but also some of the other ensemble of random graphs that have been considered before. So for example, the random Latin square graphs of Christofides and Markstrom. So all of the results that I discussed before work in this general combinatorial setup. So in particular, this key counting bound will, before we consider the counting bound for the number of subsets of the group with small product set, and now we can translate it to this upper bound on the number of subsets in this complete graph for which the set determines few colors. And we get here a bound that is of a very similar shape to what we have before in the group theoretic setting. And from this bound, we can also, again, just from the first moment method, easily deduce that in this random entangled graph, the clique and independence number is going to be of order at most log n log n with high probability. So if you are a bit careful, you can see that this resolves a conjecture of Christofides and Markstrom on the clique and independence number of random Latin square graphs. And in fact, we consider an even more general combinatorial model of a random graph, which we call a delta independent random graph model, in which all of these results also import over to that more general setup. But let me not go into more details here. So with that, let me tell you a little bit more about how we can prove this key counting bound. So we have bounded degree, edge coloring, and we want to count the number of vertex subsets determining few colors. Turns out that the key structure intermediate to this counting bound is the following structure. We can show that we have a vertex subset of size pseudo n that determines few colors, k times n many colors. Then we can find a tree using relatively few colors, where few means big O of k plus log n, that covers a significant proportion of the vertices in the set. So once you can find this, then you can do some easy encoding in order to get back this counting result. And the proof of this lemma in turn relies on the key combinatorial lemma, which, as I mentioned, I will tell you closer to the end of the talk, so stay tuned for that. So with that, let me go back to one of the points that Ben has already raised, which is this mystery of Alon's conjecture. So Alon's conjecture, if you remember, says that in every finite group G, there exists a Cayley graph that is C-Ramsey. And on the other hand, we have already seen that even for very nice group, like F5 to the D, a uniformly random Cayley graph will fail to be Ramsey with high probability. And given what we know in Ramsey's theory, if a uniformly random choice doesn't work, then it's very hard to imagine that we can do anything else to construct a good Ramsey graph. But it turns out that we can look at the situation a bit more closely and figure out a way around this. So in a finite field vector space Fp to the D, we can look at a typical sample of the uniformly random Cayley graph. It will have an unusually large clique and independent set, but we can kind of describe them fairly explicitly. So in fact, the very simple sets, like subspaces or subgroups, so in general sets with very small doubling, at the correct size, these are exactly all of the sets that account for the additional log n factor in the clique and the independence number. And you can prove this quite easily, for example, with the second moment method. So because we understand so well what are the obstructions, so what are the kind of sets that are causing the clique and independence number to be so big, perhaps we can construct a slightly modified model of a random Cayley graph in which these simple sets do not have a chance to become a clique or an independent set. And then we can hope that in this new model, we get a good Ramsey graph. It turns out that we can indeed achieve that. So over any finite field vector space Fp to the D, well, P is at least 5, so we have issues in small characteristic. We can show that there exist Cayley graphs with clique and independence number matching that of the Additive random graph. And, well, turns out that as a byproduct of the construction, for any prime that's 1 mod 4, we can construct these graphs that furthermore have the property of being self-complementary. And this comes up just because, motivated by applications in zero-error information theory, Alon and Olisky asked for the existence of such a self-complementary Ramsey-Cayley graph, and we answer the question in the positive. The self-complementary graph simply means a graph that's isomorphic to its complement. And in fact, our results, the construction can be pushed to be more general, so we can show that Alon's conjecture actually holds true in almost all abelian groups, in the sense that for almost all integers n, any abelian group with order n will admit a Cayley graph that is Ramsey. And there's nothing mysterious about this almost all here. So all that we need to do is to make sure that the order of the group is not significantly dominated by powers of 2 and 3, where we have some issues for the construction to work in low characteristic. So let me tell you just a bit about how you can modify the uniformly random Cayley graph to achieve these properties. Let's take the simple case of f5 to the d. So in f5 to the d, well, in each direction you have 2 equivalence class of elements, right? X and minus x, or 4x, and 2x and minus 2x, or 3x. And in a uniformly random Cayley graph, you would have chosen each of them to be in the generating set independently with probability 1/2. Here, all that we need to do is to introduce some correlation. So in this new model, we will pick exactly one of these 2 equivalence classes to be in the generating set, and the other will have to be outside the generating set. So what do you achieve by doing this? Well, we guarantee that this generating set is symmetric. This is for the self-complementary property, so if you don't care about it for now, you can ignore it. The key property is that if you have an element x in a generating set, then 2x cannot be in a generating set. So it comes with this negative correlation property. And once you have this property, you can use a little bit of additive combinatorics, or the Kronecker-Ruzsa inequality, and the short calculation to see that for any set A with a positive chance to being a clique in a uniformly random Cayley graph, to being a clique in this random Cayley graph, you must have that the difference at A minus A have to be fairly large compared to the size of A. It must be at least A to the 4th. So in particular, you immediately ban not only all of the subspaces, but all of the sets that behave similar to a subspace from being potentially a clique or an independent set in this model. And once you can prove this, then it's a quick calculation to see that you can recover the Ramsey property based on our previous counting result. Okay, and final quick remark I will make is that if you want to get this sharp asymptotic, so if you want to get this constant of 2 plus the of 1, then it turns out that we will need even a little bit more additive combinatorics. So the input behind this constant will be the resolution of Ruzsa's conjecture over finite few vector spaces. This was done earlier by Evan Sohar and Lovett, but we'll see, interestingly, a bit later in the talk that our perspective would also allow us to come back to Ruzsa's conjecture and resolve it in full generality. So for that, hold still for a little bit. Okay, so any questions before I switch gear to the additive combinatorial application?
Do we note for the symmetric group?
That's a good question. So, in fact, right, so I guess I should say, maybe we don't know, so let me not claim explicitly whether we know the conjecture holds over symmetric groups. But in general, the worst groups for the failure of the Ramsey property should be some group that have lots of subgroups of a certain size. And we can get certain characterization in this sense. So I think we should be able to rule out the symmetric groups from failing to be from failing to have the property that we require in Alon's conjecture. And more generally, if the group is closer to being quasi-random, if the group is very non-abelian, then these tend to help push down the clique and independence number. So we believe that only kind of the finite few vector spaces should be the worst for the Ramsey property, but we don't have kind of a very precise result towards that. Okay. Right, so with that, I'll switch gears just a little bit. And as we saw before, our key results in the previous section was already this result that I told you has a somewhat additive combinatorial flavor. It's kind of a statistical notion of structure to sets with small doubling in a group. Well, in additive combinatorics, we usually want to quantify the structure of a set with small doubling in a more quantitative and kind of to quantify this in a better way. So one of the ways in which people quantify the additive structure is the so-called additive dimension. Additive dimension, there are several notions of additive dimensions, and they are usually considered only over abelian groups. But for this talk, I will take the following definition, that is a generalization of a notion of additive dimension to non-abelian groups. So given a group G and a sequence of group elements S1 to St, we'll define the span of the sequence as the set of all possible products that you can form by taking in order the elements in the sequence to a power that is either -1, 0, or 1. So of course, if you are working in an abelian group, then you can forget about the ordering and just consider set S as a set. So given the subset A of the group, we'll define the additive in the abelian setting, but maybe in the non-abelian setting, we shouldn't call it an additive dimension. Anyway, we define this dimension d star of A as the smallest length of a sequence S for which the span of S contains the set A. And over abelian groups, this notion has been studied a fair bit. And a result of Sanders and of Shen and Shkredov shows that if we have a set A with small doubling, so either A plus A is at most Ka or A minus A is at most Ka, it doesn't matter, then the dimension d star of A have to be at most big O of K times log A. So our next result generalizes the same bound to general potentially non-abelian groups. We can show the same bound of big O of K log A for any sets A in a group G with A times A inverse at most K times A. Now we can ask if this bound of big O of K log A is tight or not. And the best example, at least that I know of, is an example of a set that you can construct even just in a finite field vector space F2 to the D, just the generic K generic translate of a certain subspace H, and you can show that in this example, the D star is at least omega of K plus log A, which can be asymptotically smaller than K times log A. And indeed, over abelian groups, can use our technique, main combinatorial lemma, to improve the upper bound on D star to K times log A plus log A. So this is only a doubly logarithmic factor away from this bound of K plus log A. And if you assume that the group G has bounded exponent, which I will define to you in a second, then we can actually achieve the correct order for the dimension d star of A. Now, one thing that is slightly unsatisfactory about the kind of structure that we have here is that, well, if I have a set A, and even if I can prove an upper bound on d star that is of order big O of K plus log A, I don't really have a very strong sense of the characterization of the structure of the set A. In particular, I will get that A is contained in a nice describable set of size at most potentially polynomial in the size of A. But this set could be a lot bigger than the set A that we start with. And in additive combinatorics, a lot of effort goes into getting stronger and sharper characterization of the structure of sets with small doubling. This will be kind of my last discussion in today's talk, and we'll see how we can get much stronger structural results for sets with small doubling and address the so-called Ruzsa's conjecture. So for this last part of the talk, we'll just be working in an abelian group G, and there's a small change from what we discussed before, it will be more convenient that we work now with the sum set A plus A instead of the product or a different set. And I'll fix the notation K for the doubling constant, which is the size of A plus A dividing by the size of A. So, as I briefly alluded to already several times, a central theme in additive combinatorics is to understand quantitatively the sense in which having a small doubling constant K can allow us to put on explicit nice additive structures on the set A. So to see how this works, let's revisit one of the classical setups, subsets of integers. If we have a set A of integers, very easy to see that the size of A plus A is always at least twice A minus 1, so roughly twice A. And if you have equality, then A has to be extremely structured. It has to be an arithmetic progression. On the other hand, if you take a set with very little structure, then the size of A plus A will be closer to the maximum, which is roughly quadratic in the size of A. So we can ask, are there more sets of integers that have a small doubling? And the answer is yes. You can consider the following class of sets, which are the so-called generalized arithmetic progression, or gaps. Such a set is described explicitly by this formula on the slide, but you can just think about taking a box in d dimension and then take a linear projection of this box back to the integer axis. Because a box in d dimension, if you add it to itself, the volume can increase by at most a factor of 2 to the d. You can see that all such sets will need to have bounded doubling as long as d is a constant. And furthermore, of course, if you take a dense subset of one of these sets, then you will also get a set that has bounded doubling. We can ask if there are more sets with bounded doubling, and quite remarkably, Freiman, in a very influential result, shows that the answer is no. So if you have a set of integers A with bounded doubling K, then A must be a dense subset of a generalized arithmetic progression P of bounded dimension. Okay, so in a qualitative sense, this completely characterizes the structure of sets of integers with bounded doubling. But we can see that here these big O of K are completely not written out explicitly. And understanding quantitatively Freiman's how big these quantities have to depend on K is one of the fundamental directions itself in additive combinatorics that has attracted lots of works. But for us today, we'll not be working over the integers. Instead, we'll be working over a class of groups that are, in a sense, even better. We'll be working with abelian groups with bounded exponent. Now say that an abelian group G has exponent R if R is the smallest integer for which every group element have order dividing R. So in particular, you can just think that the group G is given by Z mod R to some power D. That's the prototypical abelian group with exponent R. Now, in an abelian group with bounded exponent, we can see that the size of A plus A is always at least the size of A. Again, this is easy to prove. And equality can only be achieved, again, if A is extremely structured, if A is a subgroup of G. So again, we can ask this question, what are the subsets of the group with bounded doubling? And Ruzsa proved an analog of Freiman's theorem over abelian groups with bounded doubling, and he showed that all such sets A have to be a dense subset of a subgroup. So very clean characterization. And again, what we are interested in now is to understand the quantitative aspect of Ruzsa's theorem. So in particular, in the same paper, Ruzsa poses the following conjecture. Poses that if G is an abelian group with exponent R, and A is a subset with doubling at most K, then A is contained in the subgroup of size at most R to the order K times the size of A. So this exponential appears here for a good reason. So in general, again, just by considering this simple example of K generic translates of a subspace, we can show that we cannot hope for, in this formulation of the theorem, we cannot hope for a bound that is better than roughly R to the 2K. So Ruzsa's conjecture has attracted a few works in the last 20 or 30 years. So first, in his own paper, Ruzsa proved a bound that is roughly of order r to the k to the 4. Then Green and Ruzsa improved it to roughly r to the k squared. And Sanders, in his remarkable result on both the quasi-polynomial Bol-Boliov of Ruzsa's lemma, as a corollary, he can improve this bound to roughly k times polylog k, so getting quite close to a linear dependence on k. In general, abelian groups of bounded exponent, this is still the best that we know. But for certain very nice abelian groups with bounded exponent, such as the finite field vector space, we know much better. So in a finite field vector space, the first result is by Green and Tao, importing the compression technique from extremal combinatorics. And in particular, they resolve Ruzsa's conjecture for the group F2 to the D. And then later, extending this approach, Evans-Zohar and Lovett completely resolve Ruzsa's conjecture for the finite field vector spaces Fp to the D. So these two sets of results turn out to come in very different proof techniques. So the first one, which works over general abelian groups, rely on more additive combinatorial and analytic techniques. And the second school, using the compression technique, worked very well over finite field vector spaces, but they rely strongly on the vector space structure, and it's not clear at all whether this can be generalized to more general abelian groups. In particular, there are indeed problems for which groups with exponent being a composite number can behave significantly different from groups with prime power torsion, so it's not clear if these distinctions can be seen in the context of Ruzsa's conjecture. So in joint work with Jacob Fox, we prove a strong form of Ruzsa's conjecture. So we show that actually we can achieve this sharp bound of roughly r to the 2k in Ruzsa's conjecture. And again, the proof sketch, well, it comes in two steps. The first step, we apply the key combinatorial lemma, and right after this, I will tell you about it with no further delay. And in the second step, after we have the combinatorial lemma actually doing the heavy lifting, we use some additional insights from additive combinatorics that allow us to essentially bootstrap the doubling from this general parameter k to some universal constant, big O of 1. And once you have doubling and it's a universal constant, then it doesn't affect any quantitative bounding. You can use any qualitative results that you want. Okay, so this step 1 is the heavy lifting step. So with that, let me finally tell you what I hope is the takeaway message here. That's the key combinatorial lemma. It comes with a beautiful picture. So first, let me set up one notation. Given an edge coloring of a complete graph, let me denote n of AB, A and B are two vertex sets, the set of colors that appear among the edges with one endpoint in A and the other endpoint in B. So this is a segment of the lemma, so this is better because we have the figure to associate with it. So what does the combinatorial lemma say? For the setup, we have a proper edge coloring on a set of vertex set A of size little n that uses relatively few colors. So if you prefer, you can think this is exactly the setup where we have a subset A in the group where the product set A times A inverse have size at most k times n. There's one small technical condition that you can just safely ignore. What we produce is a small set of colors S. So here the colors that appear inside these small balls. The set of colors S can partition the majority of the vertex set A into a few of these balls that I call BI. And they have the following properties. So first, these balls cover nearly the entire vertex set. Right? The second property is that these balls BI, each of them can be connected by using only the colors from this small set S. And the last property is that for each of the balls BI, no matter how you select a large subset of vertices, a large linear size subset of the vertices, the number of colors between this ball and that linear size subset is at least an absolute constant times the maximum number of available colors, which is k times n. Okay, so in one way, you can intuitively think about this lemma this way. Well, really the only assumption that we have in the lemma is that we start with a proper edge coloring, which is kind of a good local condition, right? So for every single vertex, if it looks locally at the color set around itself, then it sees a lot of colors. It sees n colors. And this lemma essentially gives you an amplification of that nice local condition to these sets bi that are much bigger. And in particular, roughly you have amplified this nice condition around each vertex by a factor of k, which turns out to be very useful. Another way that you can think about these balls bi is that, well, they are kind of like central hubs that interact nicely with the remaining part of the graph, no matter how you select that remaining part. And that is going to be an extremely useful property in allowing us to, for example, build a tree that covers a large fraction of the vertices, because these balls kind of connect very well to the remaining part of the graph. So even if we choose colors randomly, we will see that the random colors will allow these balls to connect up components in a very quick manner. Okay, so roughly that's how this property is going to be useful. Okay, so give a second if you have time to read, and if you have any questions about this statement here. If you're curious, I can tell you how to apply it to really write some of the key results that I mentioned along the way.
So if you sample a set bi just randomly, does it already have the third property? Just for a single one.
So if you just go out and select randomly k vertices, then yes, k random vertices in the graph, then it should have something close to the third property. The issue is, if we just repeatedly do this independently for many tuples of k vertices, then we don't know much about, we lose this second property, which is actually also very important for the application. So the second property tells us that, well, these sets bi's are small. They possess some generic property, but we can simultaneously kind of construct all of them by using this common set of few colors. So they are very structured sets, but yet they still have this very nice kind of generic property. So that's kind of the key point. We can achieve both at the same time.
So there's no randomness or anything, it's just true, or do you assume that n is b or something? And do you assume that something, no with high probability or anything?
Well, you can see that I am hiding lots of constants here. So there are absolute constants everywhere. The proof is probabilistic. So the proof is by probabilistic method, and there will be some with high probability, but then we just deduce that something exists. And I mean, yeah, we have these constants, but they are reasonable.
The constants.
Yeah.
Can you say again how you mean this set of edges in S with colors in S partition A?
Oh.
So do you really don't want to have any others, or do you only want this property B, the second property?
So I just mean that you have these as bi that can be connected with the colors in S,
right?
And there could be there could be a few leftover vertices that I will throw away. So
right, but can we have edges with the colors in S in between the B? Then we just put them in the same B.
Right. So yeah, in our final execution, we may even allow some of these edges here without merging these B's immediately. It turns out that for various applications, it may not be useful to merge them immediately. But yeah, so don't, like, the BIs are not literally the connected components of the color set S, but something that might be a subset of that.
And anything on the sizes or the number of these sets B?
That's a good question. So as a byproduct of the proof, you can get some control on the sets B. So the BIs will typically have size on order K, which is the correct order to achieve this bound here.
Yeah.
And so there would be roughly of order n over K, many of these sets. They will have also nice structures if you want. So we didn't use it in the application, so I don't say them here. But for example, they do not only admit, you don't only have a way to connect up the sets BI using the colors in S, you have such a way such that you get a tree with small radius, so on and so forth. So there are additional properties that you can extract from the proof. Okay, so if there are no further questions for a second, then I will mention some open questions. So first, again, in a tiny bit of connection with what I will say next week, but we do know a lot now on the abstract side, on the conceptual side, about thresholds for monotone properties in general random discrete systems. In particular, that knowledge also applies to the model of random Cayley graph that we study here. But we can immediately see, just from this talk today, that the main obstruction is that even just in understanding these first moments, for something as simple as the Cliques and independent sets, we have to really work very hard. And so I think it would be a very interesting, potentially challenging direction just to study or understand monotone properties in this ensemble of random Cayley graphs in a more robust way. And in particular, can we understand properties of sparse random Cayley graphs, especially those that go beyond the spectral property more precisely. And the other open question, which I think is also very interesting, is regarding Alon's conjecture. So in our result, we address Alon's conjecture over nearly all abelian groups. But we think actually the most important case, which is still open, would be the case of the finite field vector space F2 to the D. And over F2 to the D, we can actually see that we cannot mimic the kind of construction that I mentioned over F5 to the D, simply because there is not enough room for you to introduce the easy kind of correlations or negative dependence. So, in fact, it's, there are connections to Ramsey theory, which says that over F2 to the D, in general, we cannot hope to completely avoid monochromatic subspaces of growing size. So understanding Alon's conjecture over F2 to the D seems to be a quite interesting question in itself. Okay, so with that, let me end and take more questions.
Thank you. Questions? Any questions?
So can you maybe say a few words how you did the last lemma? Very high level.
Oh, how we prove the last lemma. I see. Yes, the last lemma to prove is short but fairly tricky. So, right. So how do you... So let me first maybe quickly mention that there is a first easier version that you can prove. So if you... well, let me just go directly at it. So what you do is a random exposure process where you expose the colors, and you, from the perspective of each vertex in the graph, you try to see how the random sequence of exposed color interacts with the neighborhood of the vertex. So what we do is, let's say, we start from an arbitrary vertex V, and now we have a sequence of big O of K, many random colors that are being exposed. So what we do is, well, we sit at V, we wait until the first color that come out of V to a good vertex. So you have to, for each vertex V, we define a certain special set of good vertices. It will be a large set, and we will wait until we have the first random colors that connect V to one of its good neighbors. So you have to, so let me not go and throw on the details of what these exactly mean. And then at this point we have 2 vertices, and then we relook at this sequence of colors, there's one version of the proof which only looks forward in time. So we can just, at V2, we wait until the right time so that we can connect it to the next vertex, so on and so forth. Turns out that we'll not be able to prove the main combinatorial lemma in this way. So in the end, what we have to do is, well, at this stage, we have 2 vertices, V1 and V2, and there's a certain good set of vertices with respect to both of them. We relook at the sequence of colors from the beginning to the end. So maybe this is the color S1. There might be some point, it might be before the color F1 appears, in which we see a color S2 that connects the vertex V2 with another good vertex. So we just kind of keep doing this process where we grow the set of vertices around V1 color at a time. But the tricky part is that we do not only look forward in time, we may be forced to look also backward in time in the colors that go before the colors we see previously. So the proof is tricky exactly because of this forward-backward nature of the time, and then we have to condition carefully on a whole bunch of events to make it work. But yeah, so roughly you can take it that it's a random exposure argument and some kind of local growing of the balls BI around each vertices, but it's a somewhat tricky random exposure argument.
And can you say a little bit about how to apply it?
How to apply it? Yes. Right, so let me say how to apply it in the easiest case, which is for this fairly explicit structure that we want to produce. So for this counting result that is key in the random Cayley graph result, what we want to find is this spanning tree using few colors that cover most of the vertices. If you want to apply this key lemma to produce this, it's actually very simple. So, well, when you apply the key lemma, you get this picture already. And you can actually, well, these cover a majority fraction of the vertices. It turns out that once you can build a tree covering a constant fraction of the vertices, getting the tree to expand to a 1 minus epsilon fraction is easy. So let me ignore that. So let me just find a tree on k plus log n many vertices k plus log n many colors that cover at least a quarter fraction of the vertices of the graph. Well, let's apply first this lemma. So in here we can connect using only k colors. Now in a constant times log n many steps, in every step I just flip a random color, a uniformly random colors among all of the colors that we have. Well, each of these balls sees the rest of the graph in at least an absolute constant times the total number of colors, many colors. So there will always be a constant probability that the ball gets an edge in the sampled color to another ball. So if you keep track of the number of connected components, it is decreasing exponentially in expectation. So you can then show that there exists a sequence of constant log n many colors which will connect up everything.
Do you also show for the non-abelian case, or is there any obstacle for the non-abelian case?
For which result?
The Ruzsa's theorem.
Oh, Ruzsa's
The
theorem.
Ruzsa's conjecture, yeah.
Yeah, so, right, so I think the main obstruction would actually be was even the correct formulation of Ruzsa's conjecture in a non-abelian group, even if you assume that it's exponent. So, right, so our combinatorial lemma, of course, applies no matter which kind of group that you are working over, but there will be the second step that we need to do in order to obtain Ruzsa's conjecture, and this is kind of a wasteful step that makes explicit use of the abelian and the vector space structure. And yeah, if you have some correct formulation of the conjecture over non-abelian groups, potentially there should be a way to modify this to get the right property.
We have this lemma about number of subsets with a small number of colors. Could that be like extended to like 3 uniform hypergraph or something like that, where you give colors to
Ooh.
the triples or tripartite uniform graph.
I see.
Could that be some interesting, like, and whether the method still works or whether
I see. I think, right, that is interesting. So I think hopefully one could still push a version of this here, which is a key step towards that result, that counting result, work over higher uniformity, but I have to check the
Yes.
details of
Yeah.
that.
Right, any other? Maybe we should release him. Okay, yeah, thank you very much.